The second type of full wave rectifier we're going to look at is a bridge rectifier. So the circuit shown below here would be a full wave bridge rectifier. So immediately we notice that we have more diodes than before. We now have 4 diodes as opposed to the 2 in our center tap transformer full wave rectifier and the 1 in our half wave rectifier. And we'll talk about some advantages and disadvantages of these configurations. Okay, so in general, we're going to have 2 different cases, and what we're going to see is that now this secondary voltage Vs is going to have to overcome the V gamma of 2 diodes as opposed to just 1. So our 2 general cases are going to be Vs greater than 2 V gamma and Vs less than negative 2 V gamma. So let's look at those one at a time. So our first case is going to be if our Vs is able to overcome 2 cut-in voltages for the diode. So if our Vs is greater than 2 V gamma, our point at the very top here is going to be positive, and our point at the bottom here is going to be negative. So again, we can always come back to our diodes and think about the P-N junction. So we have P-N, 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 P-N. So we have this. And so remember, for a diode to turn on, our P side has to be more positive than our N side. And it has to be V gamma more positive than our N side. And so what we can see in this case is that for our diode D1, our P side is more positive. And for our diode D2, our P side is more positive. So in that case, our P side is at ground, but because our N side is negative, our P side is more positive. So for this case of V gamma greater than 2, or sorry, Vs greater than 2 V gamma, we can say that diodes D1 and D2 are both going to be forward biased. Now, of course, we can consider our other 2 diodes, our D3 and our D4, and using similar arguments, we can see that our P side is more negative than our N side. And so what that means is that our D3 and D4 diodes, for this first case, are going to be reverse biased. So let's quickly just kind of sketch what our circuit looks like for this first case of Vs greater than 2 V gamma. So I'm not going to draw our transformer, but let's just say we have this voltage Vs. And so this isn't necessarily just the value of, well, we can go ahead and call it Vs, but just keep in mind it's for this case of Vs greater than 2 V gamma. So it's going to be restricted to only certain positive values. And over here, let's see if I can draw this half decently on the fly. So we're going to have sort of our diamond structure. And if we use a piecewise linear model, so let me go ahead and put our resistor in the middle of our bridge here. If we use our piecewise linear model, and we're going to assume that our RF is 0 because we've not been told otherwise, we could of course adjust that. We have our D1, which was the top right diode, is forward biased, so we can replace that with a constant voltage source or a battery, value V gamma. Same thing for our diode D2, so it is also forward biased, so we're going to replace that with a constant voltage source or a battery, which also has a value of V gamma. So we're assuming these diodes have the same cut-in voltage of V gamma. Now our diodes D3 and D4 are both reverse bias, so they're going to behave as open circuits. So we get something that looks like this. So now let me connect these to our source, and of course we have a ground here, and this is our resistor. And so what we're going to see then is that if we draw in our current here, so let's do purple current, so our current is going to look something like this. So it's coming out of the positive side, going through D1, through our resistor, through D2, and then back to the negative side. So what we can note is that we have a voltage drop across our resistor that looks like this. So from positive on the right to negative on the left. Okay, so now our second case is if our voltage is negative enough to overcome the cut-in voltages of D4 and D3. So we can say if we have negative Vs is greater than 2 V gamma, and again another way we could say that is if Vs is less than negative 2 V gamma, same thing. So by similar arguments we can say in this case our D3 and D4 are going to be forward biased, and our D1 and D2 are going to be reverse biased. So it's basically just swapped roles here. Okay, so let's come back up here and let's just sort of reconsider these points. So now we're saying at this top point, this is going to be more negative, and at this bottom point, now it's more positive. And so of course we can see again that this is going to mean that our P side of D4 is more positive than our N side, so it's forward biased. Our P side of D3 is more positive than the N side. Again, the P side is grounded, but our N side is at a negative potential. And then the opposite is true for our D1 and D2. Their P sides are more negative than the N sides, which means that those two diodes will be reverse biased. Okay, so again, we can sort of sketch this the same way we did in the previous case. So let me do that real quick here. So we have, again, our voltage source, Vs, but we're limiting this. So using this same thing up here, we can say this is for Vs less than -2 V gamma. So just rearranging that inequality above. And again, let me try to sketch real briefly here. Let's put our resistor across the middle of our bridge. And now our D3, so let's look at the direction. So we've got a positive on this side. So we get something like that. And again, we're assuming they all have the same cut-in voltage of V gamma. And D4, positive on this side. So we get something that looks like this. And we have this grounded, and our other two diodes, D1 and D2, are behaving like open circuits because they are reverse biased. So let's connect that to our source. I know that drawing is a little bit rough, but hopefully you can see what's going on there. So now let's do this current in green. And so now what we see is, of course, really with this Vs being negative, our polarity is going to be like this. So our current is actually going to be coming out of this direction. And we see it's going to be going here, through our resistor, through our D3 diode, and then back into this negative terminal here. So we can note that the voltage drop is in this direction across our resistor. And so of course what we can note comparing these two is that our V0 is the same polarity in both cases. Or we could also say that in terms of current. We could say current direction through R is the same in both cases. And so that's where we get our full wave rectification from. Okay, so again, we can look at this graphically. And so what I've actually done is I've just copied sort of our waveforms from our previous discussion, but I'm going to highlight a couple things that are different here. So because we have to overcome 2 V gamma as opposed to just V gamma, note that these points here are now 2 V gamma and -2 V gamma respectively. And what that means is that the difference between our peak values of our output and our Vs is 2 V gamma as opposed to just 1 V gamma for our center tap transformer circuit. Now for this first part of our first sort of rectification part here, we have D1 and D2 that are conducting. For our second part, we have D3 and D4 that are conducting, and then it just alternates. So D1 and D2, D3 and D4, D1 and D2, and so on and so forth. So now let's real briefly talk about some advantages and disadvantages. So one thing that sort of gets lost in the fact that I just copied this figure directly is that if we think, of course, if our Vs is staying the same, so let's say this top dashed line here and this bottom dashed line are staying the same, and our V gamma is the same, we just multiply it by this 2. Well, what's going to be happening is this dashed line is going to be going up, and this dashed line is going to be going down. So what that means is that we're going to have less time on, because so let's just sort of look at an extreme example. So let me let's do this. So let's say if our 2V gamma line more realistically was something like this. So what we can see then is that our diodes D1 and D2 aren't cutting on until later, and they're cutting off sooner compared to if we just had 1V gamma. Now, what that means is we're going to have less of our cycle time on, so we're going to be sort of wasting more of that time as opposed to our center tap transformer. Another thing is that, of course, our V out is dropping further. So let me come back to our normal color here. So because we have this 2V gamma drop, that could become more significant and more problematic, particularly if we have lower voltages for our VS max. So for instance, if we have something like a 10 sine omega t as an input at our VS and our V gamma is 0.7, well, 1.4 is, that's almost getting close to 15% of our max value, so that's maybe not negligible. Whereas if we had, instead of 10, maybe this is 30, then 1.4 isn't as big of a deal. So we kind of have to think about where we're using this. So those are maybe a couple advantages of the center tap transformer. So now we can talk about advantages of this bridge rectifier over our center tap transformer. So advantages over center tap transformer rectifier. And so of course both of these full wave bridge rectifier or full wave rectifiers, the center tapped and the bridge, have the advantage of being more efficient than our half wave rectifier. So the bridge rectifier is going to require only half of the turns in our secondary winding. Because we're not having to produce 2 VSs, we only need 1 VS. So only about half the turns in our secondary transformer winding. And so ultimately, of course, what that translates to is less cost. We don't have to have as much material to create that winding. Secondary transformer winding. We don't have to take up as much space putting more windings depending on the size of this transformer. Another key advantage of our bridge rectifier is that PIV is lower for each individual diode because it's basically being split between two diodes as opposed to just one diode for each case in our center tap transformer. So our PIV voltage seen by each diode is 1/2 the PIV in our center tap transformer circuit. So what we're going to do in the next video is we're going to come back and we're going to briefly talk about how we can take all of these waveforms that we've looked at so far, so in this case this green waveform shown here, and make it a little more conducive to something that needs a constant DC voltage.